Hey everybody, unit vocabulary for organic. This would be video 2. Got to get through the vocab so we can get through that quiz and understand what we are talking about for this unit. Definitely some specialized words. Homologous series, there's one we've never seen before, but we do know that homo does mean same. This is a reference table Q. This is the homologous series, and you're going to see there's some hidden information in here where alkanes are single bonds between the carbons, alkenes have the double bond between the carbon, alkynes have a triple bond between the carbons, and that's what I'm really going to need you to pull out. And then we'll get to that general formula also. How do we figure out how many carbons to how many hydrogens? And those mathematical formulas work out where N is the number of carbons. Okay, and we will use this quite a bit until we get thoroughly versed with anes, enes, and ons. And this is a group of hydrocarbons with similar chemical formulas. Table Q. Okay, homologous series. Organic prefixes, whole nother reference table. This is 2 of 3 that are super important to the whole unit. And as you can see, the prefix itself, meth is 1, eth is 2, prop is 3, bute is 4, tells us how many carbons. So this is the word that tells us how many carbons are in the backbone of the molecule, reference table P. Okay, and we're going to get right to it. The next one is table R, organic functional groups. These are the things that make us different than just a hydrocarbon. So I don't have just hydrogen and carbon. I have something else, generally oxygen or nitrogen or a halide. The part of the molecule that makes it different from plain hydrocarbons. This classifications are based on the placement of the O or the N, table R. And it could be a bromine or a fluorine also. It's not limited to O or N, just a lot of them have those. Okay. Alkanes, specifically saturated hydrocarbons that have single bonds between the carbons. That means there's plenty of parking spots for hydrogen and it fills up. It is saturated. Okay. Hydrocarbons that contain all single bonds between carbons, you can make a side note that they are saturated. That's the kind of side note that I'd appreciate you putting in here. That will not be on the vocab quiz, of course, but will be thoroughly discussed as the unit goes on. You'll need to understand the difference. Okay. Alkenes, notice these all have at least a minimum of one bond. One double bond. And we'll learn how to name that to show that the ene shows us that there's a double bond, and then the address of that double bond. Okay, that butene in that example is not actually how I'm going to teach you how to write that. Okay, these are hydrocarbons that contain at least one double bond between the carbons. Could have 2 double bonds, could have 3, but there's a minimum of 1. Once there's 1, it becomes an ene. And ines, as you can see in this picture, all have triple bonds, and you can start to see that there's some numbers on there where the address tells me which carbon that triple bond resides. Okay, these are hydrocarbons that contain at least one triple bond between their carbons. Okay, good. Structural formula. This is the structural formula. We draw structural formulas, and this tells me not just how many of each atom, but the kind of bonding that exists in their spatial arrangement. So a structural formula actually gives me probably the most information because it helps me see the bonding and the arrangement in space. This is a diagram that represents the number and arrangement of atoms. Okay, probably the most information out of all of them. The molecular formula is something we're very familiar with. This is just writing out the number of atoms, but it doesn't tell me anything about where they are. Okay, so this is a symbol that shows how many of each element in the molecule, but that's it. I don't see the bonding. I'd have to build it from that, and that's where I'd have to infer some things. You see what I'm saying? We'll learn how to do that too. Isomer, key vocab word. An isomer is, if you look at all these pictures, there's the same amount of things. Where there is the lines crossing is carbons in this particular picture. What it is 2 molecules that have the same number of each atom, same number of carbons, hydrogens, and oxygens, but different arrangement. We call that an isomer. Okay. By definition, we'll play some games with those. Straight chain hydrocarbon, just like it looks like. It's a straight chain of carbons. We need to be able to count that base straight chain because that's going to be the backbone of our molecule, and that's going to affect our naming. a simple hydrocarbon chain that has no side chains or functional groups. Okay? Straight chain hydrocarbon. A branched hydrocarbon literally is what it sounds like. It has a branch sticking off of more carbons. But notice it's still just carbons and hydrogens, hence branched hydrocarbon. Okay? Hydrocarbon chain that has one or more carbons attached to the side of the chain. It is not just a straight chain. Okay? There's branches, just like in a tree. Okay? Saturated. This word saturated means just what it meant in solutions, except for now we're talking about hydrogen. So when I am single bonded, if I'm an alkane, the carbons are holding the total amount of hydrogen it possibly could when all makes 4 bonds. So this is a hydrocarbon that holds as many hydrogens that it possibly can. It's got to be an alkane, which means single bonded carbons. Therefore, I have room for all the hydrogen I can possibly hold. Okay. Moving right along. Unsaturated hydrocarbon then is not, of course, holding as much hydrogen as it could. And in this case, with 2 carbons, I should be able to hold 6 hydrogens. And you'll learn the math, it's not that hard. Because of the double or triple bonds, I'm holding less hydrogen. If I break those bonds, I can insert hydrogen, and now we're talking about an organic chemical reaction. See how this works? This is fun chemistry stuff. Hydrocarbon that does not hold as many hydrogen atoms as it can. Hence, alkenes and alkynes is how we say that. Polymerization reaction. Polymer means many, and this picture is just many of the same thing linked up, and that's literally what it is. This is a reaction that links many of the monomers together in a large chain. Monomer is one, poly is many. I take one monomer and link it to another monomer and to another monomer, and I can grow that chain, and that is a polymerization reaction. Okay? Fermentation. This is how we make wine or hard cider. This is a reaction between an enzyme that reacts with sugar to make alcohol. Okay. My personal favorite and most people's favorite is the good old-fashioned combustion reaction. You need to be able to pull this one out. This is a reaction that burns any hydrocarbon in the presence of oxygen. So oxygen is a reactant, forming specifically carbon dioxide and liquid water. Every time. Carbon dioxide and water, if they're your products, and oxygen is a reactant, it is a combustion reaction. You need to be able to pull those key pieces out and call that a combustion. Fair? Saponification. This one's tough because we don't know what that word saponification is. It doesn't even make sense. It is soap. So specifically, when I react a base with a fat, I make soap. Number 1 rule of Fight Club is we don't talk about Fight Club. Esterification makes esters. There you go. And here it is. It's an organic acid with an alcohol, makes an ester in water. It's what we call a dehydration reaction. It's going to take the H off of the one, the OH off of the other, forming HOH, which is water. And then where it pulls those apart, the 2 molecules link together, and that's called esterification. It is a form of dehydration synthesis, a reaction where an organic acid reacts with an alcohol to make an ester. Doing good, and I believe we are almost done. Substitution, So here's a switch. This is like a single replacement reaction, right? One Cl and one H are going to switch if you look on the product side. Okay, so there's a switch, there's a substitution going on. This is a reaction where an atom of one molecule switches with the atom of another molecule. They substitute for each other. Where an addition reaction, you see how I have a double bond in my carbon. If I open that up, I have parking spots, and now I can put both chlorines in. There is no switch. There is a straight addition, and that's it. So that's two more. This is, I think, all of the actual 7 organic reactions. So we will get to those at the end of the unit and do a poem. Okay, and I think we are done. That's it. So study for your vocab, and I will see you guys in class.